Give me some more details. Yes, sir.
The S2 orbital is a lot larger than the S1 orbital.
Okay, so we've got, and what's it shaped like? It's just a sphere. It's a big old beach ball. So that's the 2s. What about those 2p's? Give me more information. Yes, sir.
There's 3 different ways to write them.
Well, because there are 3 of them.
3 of them, yeah.
So what do we have?
Your PX, which goes left and right. Your PY, which goes up and down. And your PZ, which goes back and forth.
Okay. So we have a 2px, a 2py, and a 2pz. Okay. How many of you had that? Okay, so you know that there are 4 orbitals on the second man energy level. How many electrons can each of these orbitals hold? There was a trend. 2. They can all hold 2. 1 up, 1 down, 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. Okay, good. Good, good, good. Okay, so we were starting to build this sort of little thing here. This platform going up with the 1s, the 2s, the 2px, the 2py, the 2pz. We had gotten to the 3s. And the 3s, of course, is a little bit bigger than the 2s. You know, it's a bigger beach ball. The same holds true for the p's. They're slightly larger dumbbells. So we've got 3px, 3py, 3pz, and then we're on to the 3ds. And we don't even try to write the actual axes for these. We just name them 3d1, 3d2, because it gets too wacky and weird if we try anything else. So we've got leaning back, we've got flat looking at us, we've got sideways on, and we've got donut and dumbbell. So 3d1, 3d2, 3d3, 3d4, and 3d5. Guess how many electrons each of those orbitals can hold?
2.
Just 2. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Yes, sir. Okay, so we could keep going up to 4 and 5, whoops, and 6 and 7. We're not going to, because it just gets too insane. But now we want to start to talk about the rules for how we do choose where these electrons go, because there are actually rules for this. So let's go back to this. Okay, so now we're going to start to figure out where each of the electrons in a given atom lives. How do you figure out how many electrons an atom has? Not charged, because right now we're just talking about neutral atoms. We haven't even started to talk about charged atoms yet. So the pieces of information that you typically have about an atom, and you did a lot of this in the Chapter 3 stuff, you have atomic number and you have atomic mass. Which one of those gives you a clue about how many electrons something has?
Atomic number.
Why? Okay, hold on. Don't holler out. So, I will say that atomic number is the right answer. What is the atomic number equal to? Don't yell it out. Jot it down and then compare notes with somebody sitting near you. See if you're thinking the same thing they are. Atomic number is the number of protons, and in a neutral atom, that's also the number of electrons. So we know how many electrons any atom should start off with. Now, we've done this chart. We've filled in lots and lots of electrons. There are actually rules for where they go and how they fill in, so let's get started with those. We'll start off with a piece of information that you've already figured out just observationally. Guess how many electrons any orbital anywhere in an atom can hold? 2. The maximum number of electrons that an orbital can hold is 2. All orbitals can hold 2 electrons. So how many electrons can an orbital hold? 2. 2, not 3, not 1. 4 is right out. 2. Any orbital. I don't care if it's a 1s or a 5d or a, 7g. Each individual orbital can only hold 2 electrons. Just 2. They can hold 2 electrons. So, quiz, quick quiz. How many electrons can any orbital hold? 2! Okay, good. I think you have it. 2 for my smart alecky chemistry students. 2! So, okay, because we know how many shapes occur on every main energy level, right? On the first main energy level, how many shapes can you have? 1, and it's a sphere. On the second main energy level, how many shapes can you have? 2. How many shapes? 2. You can have the sphere and you can have the dumbbell. On the third main energy level, how many shapes can you have? 3. Seeing a trend here? Uh-huh. How many shapes can we have on the fourth main energy level? 4. How many shapes can we have on the fifth main energy level? 5. This is all very basic math. The number of shapes possible is the same as the number of the main energy level. Okay? So on your tests, I will ask you questions like, on the sixth main energy level, how many shapes of orbitals are possible? 6. Okay. Now, let's look back. Okay, but what did we say about how many actual orbitals there are? Whoa. So we said that if there's more than one orientation for that orbital, then we'll have more than one of it. So for the s orbital, how many orientations are there?
1.
Just 1, so there's only one s orbital. So first main energy level has 1 shape, and how many actual orbitals?
1.
Just 1. So shapes, actual orbitals. Rah! Okay, on the second main energy level, we have 2 shapes. We have the sphere and we have the dumbbell thing. How many of the dumbbell things do we have? Because there are 3 ways to orient them, so we have 3. So our total number of actual orbitals is 4. We have 1 of those and 3 of those. So 4 actual orbitals. On the third main energy level, actual orbitals, we have 1 of the s's, we have 3 of the, let me draw that the other way so it's not so confusing, 3 of those, and we have 5 of these weird things. So 1 plus 3 plus 5 is how many? So we have 9 actual orbitals. Anybody see a pattern yet?
It's square.
Yeah. Whatever this number is, the number of actual orbitals is just n squared. So, how many actual orbitals do you have on the fourth main energy level? 16. How many actual orbitals do you have on the 25th energy level? 25. Nice pattern. So on your test, I will ask you things like, on the second main energy level, how many orbitals are present? 4. Okay. Now, because every orbital, no matter what it is, can hold 2 electrons. Let's do some moving. If every orbital can hold 2 electrons, and you have 1 orbital, how many electrons can you hold? How many electrons do you have? 2. If every orbital can hold 2 electrons, and you've got 4 orbitals, how many electrons can you hold? 8. If every orbital can hold 2 electrons and you got 9 orbitals, 18. What about the fourth main energy level? How many electrons can you have there? 32. And on the fifth main energy level, how many electrons are possible? 50. Now, this is only how many are possible. Not all these are filled up in most atoms. So the number of electrons possible is 2n squared. Okay? So n is equal to the main energy level, and the number of shapes is equal to n. The number of actual orbitals is n squared. The number of electrons possible is 2n squared. I will ask you questions like, on the fourth main energy level, how many electrons are possible? How many electrons can be held on the fourth main energy level? Yeah, 32. But you have to know those relationships. So that's just reiterating the pattern we saw. We could do a sample here. So for main energy level 3, how many shapes? 3 shapes. How many orientations, how many actual orbitals? 9 actual orbitals. And how many actual electrons? 18. Okay, pretty easy. This is actually a good time to introduce your learning goals for the week. So I'll be sticking these up front. We've missed them for a few weeks because we were so stuck on atomic history. But you've got 3 learning goals for this week, and they'll spill over into next week, and I will stick them on the board. Represent the electrons in any atom using 3 forms of notation. We're about to start on those. Explain how and why the pattern of electrons in an atom affects how reactive it is or isn't. And predict patterns of electron configuration using the periodic table. So by the end of this week, you should be well on your way to those 3 things, and I will stick them up on the wall. First, we got to know what electron configuration is. All of this is the pattern of electrons that are present in an atom of a given substance. So for every substance, for gold, for aluminum, for carbon, for oxygen, there is a pattern of electrons that occurs in every atom of that substance. And you talked about this a little bit in physical science, typically, using the Bohr model. We're going to step it up a notch because, of course, now we're using the quantum model. We know about orbitals, and we're going to place electrons correctly in those orbitals. What orbitals are full completely governs how an atom behaves. And you know already that some atoms are much more reactive than others, and it's all about giving up or gaining electrons or getting to something that's stable. So we figure out their electron configuration using a set of 3 rules. And I like things like this because it's just like, okay, you check off the rules, you go through the rules, and you have it right. Easy breezy. Okay, so the first rule that governs how electrons go into orbitals is called the Aufbau principle. I'm less concerned that you know the names of these principles than I am that you're able to use them. Aufbau just says an electron is not going to go any higher in energy than it has to. It's going to take the lowest possible orbital, lowest energy orbital. So 1s will fill up first. And the metaphor I like to use here, because most of you will be going off to college and many of you will be living there in the next few years, is that we've got a dorm, a high-rise dorm. And you're showing up for college carrying, your refrigerator, all your suitcases, your pet hamster in a cage on your head, your little electric teapot and your microwave. You don't really want to climb any more stairs than you have to. So if there's a room open on the first floor, you're going to take it because you don't want to climb the stairs. If everything on the first floor is full, you'll go to the second floor. And if everything on the second floor is full, you will go to the third floor. But you're not going to go any higher than you have to because you want to save yourself work. So all this says is that you go into the lowest energy spot that's available to you. And electrons do that. Now, this is really easy up to 2p. Yeah, you knew there'd be a catch, right? So the 1s is the lowest energy orbital. And as we've been talking about these things, remember we've been building our little diagrams like this so that we get that we're climbing in energy. After the 2p, when we get up to the third main energy level, there's some weirdness. And, well, let me just show you the diagram first. Have you seen this diagram before? Okay. You will learn to draw it. You will actually get 2 points for drawing it on your test at the end of this chapter. You will learn how to draw it. You will be really good at it. You'll get to the point where you'll be able to draw this at 2 a.m. woken out of a deep sleep with no caffeine. I promise. Let's start practicing. So this drawing goes in order of, it's sort of upside down from an energy perspective, and we start with the 1s, and that's the first one that electrons go into, the first subshell. And the next one is 2s, and then we have 2p. Well, every single main energy level has an s orbital. So we'll go ahead and draw these all, or write them all. 3s, 4s, 5s, 6s. We don't usually go above 6s. I mean, there is a 7s. We could draw it, but we're never really going to talk about electrons that live there. So all of those are also going to have a p orbital, or a p subshell. So we have a 3p subshell, and a 4p subshell, and a 5p subshell, and a 6p subshell, and of course 7, though we never really talk about it much. Well, starting on the third main energy level, what do we add? D. So we have a 3d subshell, and everything above 3 will have a d subshell. So we have 4d, and 5d, and 6d, and 7d. What do we add on the fourth main energy level? F. So we have 4f, 5f, 6f, and 7f. This is traditionally about as far as it gets drawn out. If we wanted to really be nitpicky, what do we have starting on the 5th? Do you remember? I told you we'd never talk about it, but we have G's. So we could go 5G, 6G, 7G. I don't know what comes after G. I don't want to know. It's probably, you know, some freaky, crazy, wild, hairy, pointed, spiked, frightening kind of shape, and I don't want to know about it because it'll give me nightmares. So now that we've drawn all these, we can draw lines through this diagram. It'll actually show us the order in which these things fill. So I'll go ahead and use a bright yellow. I think that'll show up nicely. So we start each of these lines just like that. And we go down through 1s, down through 2s. So far we're saying that 1s fills, then 2s fills, then 3p fills, 2p, then 3s fills. And so far this is nothing that's not expected, right? Well, then when we get to 3p, after 3p, the 4s orbital fills. 4s fills before 3d, because 4s is actually slightly lower energy than 3d. And after 4s, we fill 3d going into 4p, and then going into 5s. This is why you have to learn to draw this diagram, because there's no way to remember these without the diagram. After 5s, we start filling 4d, then 5p, then 6s. And if we get something that's actually all the way up to 6s, after 6s, we start filling 4f, 4f, 5d, 6p, 7s. So they're pretty weird when you get down here. That said, we typically don't go much higher than our 4Ds. You know, I'll probably give you a bonus problem at some point that gets you out into the 7th man energy level. But, you know, we definitely concentrate on the upper part of this diagram. Now, how can something that's on the 4th man energy level be lower energy than something that's on the 3rd man energy level? So in terms of using a visual metaphor for this, let's go back to the idea of our apartment building, or our dorm building. And the weird thing about this dorm building is that the floors are on a slope. Okay? So here's the first floor, here's the second floor, here's the third floor, here's the fourth, oops. Here's the 4th floor. If we divide these up into rooms, and we look at this as though it was energy levels. This is definitely the lowest energy level, this big room down on the 1st floor. And then this is the next lowest energy level. So this would be our 1S, this would be our 2S, this would be our 2P. And if we say that this is 3S, it's still, well, I drew that badly. Okay. Let's just focus on 4S and 3D. What we're saying is that the floor of 4S starts at a lower energy level than the floor of 3D. Okay? So it's this sort of weird differential. So 4S, this little room right here, the elevation of the floor in 4S is actually lower than the elevation of the floor in 3D. It's a lower energy level. There's no great, I mean, this is the best visual metaphor I can come up with. It's a little complicated to understand. It's mostly just something you have to kind of memorize and accept, unless you really want to go into particle physics and you want to look at Schrodinger's wave equations. I consider that to be above my pay grade. So that's the visual metaphor, but really that's the important part, that you just have to kind of memorize that this is the order of increasing energy as those lines go through, and that's the order they're going to fill in. Okay? So Aufbau just says if there's a low energy orbital available, you'll take it. You'll take the lowest energy orbital available as an electron. Okay, rule number 2 is the Pauli exclusion principle. This is this address metaphor, where we have to have different pieces of information to identify an electron, and all Pauli is saying is that within any given orbital, so if this is a 2s orbital, one electron has an upspin, one electron has a downspin. So it's just a way of differentiating them. And again, remember, spin is not literally like little things tumbling in a dryer. It's sort of a physics metaphor for the orientation of electrons. Again, beyond the pay grade of all of us. Last rule, and then we can start placing electrons. If you've got 3 orbitals that have equal energy, they're all going to get 1 electron before any of them gets 2. We're back to the dorm room metaphor. So if you show up at your dorm on the first day, we'll draw our weird slopey room, and there is already, so we've got 2 people, which are actually electrons, on the first floor. So you have to climb to the second floor, you know. And there are 2 people on that first part of the second floor, and you have to go, so this is our 2s orbital, of course. If you have to go up to the 3p and there are 3 rooms and they're all on the same level, no more stairs are involved, and there's one person in this room, Do you really need a roommate? If you could have a room all to yourself, maybe? If you got a chance to have a room to yourself, you're going to take it. So you're going to keep moving. If you show up and there are 3 rooms and there's already somebody in the first 2, and taking the 3rd room all to yourself doesn't involve any more steps, you're going to take it. Now, if we get to this point, and there's 1 person in each of those rooms, and it would take additional stair climbing to get to a room by yourself, yeah, fine, you can deal with a roommate. And you'll start to fill in those. So all we're saying is, if you've got 3 orbitals that are equal energy, the same subshell, or 5 or 7, they're each going to get 1 electron before any of them double up, as far as that goes. So let's practice actually using these rules. Okay, the first way we're going to practice, we're going to learn 3 forms of notation for electron configuration, for the pattern of electrons in an atom. And the first one we're going to learn is called orbital notation. So in orbital notation, you actually literally draw every single orbital. Sound like a lot of work? Sound like a pain in the butt? It is. It's the longest and most detailed version that we'll learn, and then each one after that is kind of a shortcut. So we start off, when we're doing orbital notation, we literally write the orbitals in the order that they would fill. And we draw a blank line over the name of each of them to indicate the orbital. 2px, 2py, 2pz. So let's start off with something that has 6 electrons. That would be carbon. Okay, 6 electrons. So based on our rules, where's the first place electrons are going to go? 1s, lowest energy available, Aufbau. So we put in 1. Would it involve stair climbing to get to 2s? Yes. So we're going to fill 1s before we go on to the next level. So now we have 2 electrons placed. Where's the next place electrons are going to go? 2s, next energy level. Okay, we got 1. Where's the second electron going to go? Right next to it. So we're up to 4. We have 2 more electrons to place. We know that they're going to go to the 2p subshell. We're going to put 1 in 2px. Where does the next one go? 2py. Because we're not going to put 2 into a single orbital until we have no choice. So this would be the correctly drawn orbital notation for something that has got 6 electrons. We are now going to just practice orbital notation. Okay, we have something with 14 electrons, silicon, Si. So we're going to draw, the first thing you should do whenever you're doing these is to reproduce this little thing. Because doing so tells you, where the electrons are going to go. Okay, so having drawn the Aufbau diagram, I'm going to start out drawing the orbitals in the order that they would fill. 1s, 2s, 2px, 2py, 2pz. What comes after 2p? 3s. 2, 4, 6, 8, 10, 12. And what comes after? I heard someone say 3px comes next. Well, that's true, but we have to draw the whole darn subshell. Y, 3p, z. Even when we're going to leave some of those blank. All right, so let's start filling up electrons. 1, 2. Next 2 go. 3, 4. When you fill your P's, please, please, please get in the habit of doing that. Don't shortcut it and go, I know I'm going to fill it all up. It's a great way to screw yourself up. So now what are we up to? 2, 4, 6, 8, 10, 12. We can do that in the S because we know that there's nothing else in that subshell. And now we're up to 12, 13, 14. Okay. Why do you have to draw the 3pz? Because this is a subshell, and we always draw a subshell. If we draw one orbital in a subshell, we draw them all. So those are the little subshells. And if we wanted to look at main energy levels, let's do this in something nice and bright. Does that show up well? Yeah. So there's the first main energy level. There's the second main energy level, composed of those two subshells. There's the third main energy level, and of course we're missing the 3D subshells. We didn't draw those. Does that make sense? Okay, so I'm going to give you some practice problems and time to practice.